Hello everyone, a very good evening. Welcome to the ACE Engineering College YouTube live sessions. These sessions are useful for all the engineering students because in these sessions videos we are discussing about the questions and answers which was asked in the previous year's examinations of university. So in these sessions we are not only discussing about the question and its answers, but also we are discussing about the tips and tricks to be followed while writing the examination. That is, when we see a question in the exam, we have to know that how efficiently we can write the answer in a stipulated time. So all these things will be discussed in these sessions. So I request all the engineering students to go through these full videos and perform well in your respective examinations. Now coming to today's session, myself Abinay, I am the faculty of ACE Engineering College. Today I am going to discuss about the topic combustion in IC engine, which is a topic from the thermal engineering one subject. Now basically what is meant by combustion? Combustion is nothing but a chemical reaction takes place between the fuel particle and the air particle. So a chemical reaction takes place between a fuel and a oxygen particle. So because of that chemical reaction, it results in release of the heat. Results in the release of that heat, and that chemical reaction, as it is releasing the heat, it is called as a exothermic reaction. So in this because of this chemical reaction, the heat energy is generated inside the engines. This is what the combustion is. Now in this combustion concept, we are discussing about the IC engines. So basically we are having two types of engines. One is spark ignition engine. The other one is the compression ignition engine. Now in this spark ignition engine, in the last session we have discussed about how a spark ignition works. That is, the combustion is initiated with the help of a spark plug in the case of spark ignition engine. Whereas compression ignition engine, that also we have discussed in the last session. So in the compression ignition engine, the combustion will be takes place because of the auto ignition of fuel and the air. So here the combustion process is different in spark ignition engine and it is different in the compression ignition engine. So in this session we are going to discuss about the stages of combustion, how the combustion is happen in stages separately in SI engines as well as the CI engines. Now abnormal combustion in the SI engines, in the CI engines, and also the phenomena of knocking in the SI engines and the CI engines. This topic, the phenomena of knocking, is the most important one with respect to the IC engines, and also finally we will be discussing about the combustion chambers in SI engines and CI engines. Now let us see some previous year's questions asked in the university examinations. The first one was write about the homogeneous mixture and a heterogeneous mixture. So in which engines it is used, and with respect to SI engines we got one question like different stages of combustion in SI engine and also the abnormal combustion in the SI engine, and the factors which affecting the flame speed, and finally various types of the combustion chambers. Now these questions are previously asked questions from the topic of SI engines. Now coming to the CI engines combustion, it was asked like this, that is, describe the phenomena of knocking in diesel engines using P theta diagram, and also asked about the various types of combustion chambers in CI engines and factors affecting the delay period, and lastly the comparison between the normal combustion phenomena in SI engines and CI engines. So in this way the questions were asked separately in the SI engines and the CI engines. Now let us start with the first one, that is, what are homogeneous and heterogeneous mixtures, in which engines these mixtures was used and explain. So first we'll know about the homogeneous mixture. See here homogeneous mixture means when the two components are mixed, those two components are uniformly distributed. Now after the mixing, if I want to see the individual components, it cannot be seen, that it cannot be visually distinguished. So this type of mixture is called as homogeneous mixture. For example, take the salt water. When you mix the salt in a water, after mixing, what happens? If I want to see salt and water separately, it cannot be seen. So that is the example of homogeneous mixture. Then what is a heterogeneous mixture? In this, the two components are mixed. Now even after mixing also, the evenly distribution will not be possible in the case of heterogeneous mixture. Now after mixing, we can see the separate two components individually. So this is heterogeneous mixture. Example is the mixture of oil and water. When we mix the oil and water, after mixing also we can able to see the oil components and the water particles. That is an example of heterogeneous mixture. Now in which engines these mixtures are used? Now let us start with the homogeneous mixture. These mixtures are used in the spark ignition engines, and as we have discussed in the last session, the spark ignition engines, what happens in that? The fuel and air thoroughly mixing takes place before entering in the combustion chamber. Now because of the thorough mixture, what happens? It is evenly and uniformly distributed. The air and the fuel particles mixing, because of that mixing, it is evenly and uniformly distributed. Now because of this even and uniform distribution, it leads to the efficient combustion. Again, because of the efficient combustion, by which the engine operation will be very smooth with very good fuel economy, right? So this is what happens when we use a homogeneous mixture in spark ignition engines. Now what about heterogeneous mixture? These heterogeneous mixtures are used in the compression ignition engines. This working also we have seen in the last session. Okay, now what happens in the compression ignition engine? Air enters during the suction stroke or the intake process, whereas the fuel enters in the combustion chamber directly at the end of compression stroke. Now here what happens? During compression process, at the end of compression, when the fuel is injected, at some places the fuel concentration will be high, at some places the fuel concentration will be low. So there will be a varying fuel concentrations in various regions in the combustion chamber. So because of the fuel concentrations is varying in the various places of the combustion chamber, when the combustion is done, what happens? The pressure will be increasing. So there will be a varying pressure rise in the various regions. So because of this, these engines are made as a robust engines, and these engines can able to handle wide range of operating conditions. That is why these compression ignition engines or the diesel engines are well suited for the purpose of heavy load applications like heavy duty works and constructional equipment. So this is about the heterogeneous mixture. Now coming to the combustion in SI engines. Now we have discussed about the combustion and the working of SI engines in the last session. Now what is this combustion in SI engines is? Now when the combustion happens generally at the end of compression stroke with the help of a spark plug. End of compression stroke with the help of a spark plug, a small spark is created. That spark creates a flame, and that flame will be a turbulent flame. Okay, now because of the spark plug creates a flame, that flame will be a turbulent flame, and that will be propagated inside the cylinder by burning all the fuel particles inside the combustion chamber. So this process happens inside the SI engine. Now when all this process have been combined and it has made into a diagram, that diagram is called a P theta diagram. P theta diagram. Now let us discuss about this theoretical P theta diagram. Now in this figure, if you see, suppose here here 0 is the crank, x-axis is a crank angle, y-axis is a pressure. 0 angle is nothing but the position of BDC. 0 angle is a position of BDC. 180 angle is a position of TDC. Okay. Now during compression stroke, piston will be moving from BDC to TDC. That is called as this compression process. Okay. Now when the piston reaches this B point, that is to the near to the TDC, the spark is generated. Because of the spark generation, the charge present in the cylinder tends to combust, by which the pressure will be increasing. Here you can see the pressure increases from B to C. This is a process of combustion. Okay. Now after reaching the maximum pressure, that means after burning all the fuel particles, piston tends to move from TDC to BDC. That is called the expansion process, where the volume of the cylinder will be increasing and the pressure reduces. Now this is a theoretical P theta diagram. Now in the actual engines, it won't be like that in a smooth and uniform manner. This process, entire process will be divided into stages. So let us see the actual P theta diagram. That means in the stages of combustion in SI engine. Now this is a figure where x-axis is a crank angle, y-axis is a pressure. Now the piston again, in this actual one, the piston will be moving from BDC, from the BDC to that means BDC crank angle towards the TDC, that is a TDC, it is taken as the 0 angle. Now it is moving. Because of that, what happens? Initially the pressure will be increasing. That is when the piston is moving towards the TDC, when it reaches near to the TDC, at this point, near to the TDC, at point A, what will be happen is spark will be created. This spark will be created at point A. Wow. Now when the spark is created, what happens inside the cylinder? Immediately the charge won't burn. The charge will take the heat from the spark and it will reach its self-ignition temperature. Then it will start exploding, that is burning. Now where the particle starts burning, that is point 2, point B. Okay. Now this A and B is the stage 1. A and B is the stage 1. Whereas now at point B, the combustion has been initiated and whatever the fuel present inside the cylinder, it tends to burn at a very fast rate, which causes the pressure to rise rapidly. So here from B, the pressure will be increasing in a very less time to reach the point C. Okay. Now this BC is a second stage. Now when the maximum pressure has been reached, that means maximum fuel particles will be burned inside the cylinder. Now after that, the piston will be traveling towards the BDC again, which is an expansion stroke, and during that stroke the volume is increasing and the pressure reduces. Now during that stroke, if there is any fuel particle left, that will be burned and that reaches to the end of combustion at point D. So here we are having 3 stages: stage 1, stage 2 and stage 3. Now what the names for the stage 1, stage 2, stage 3 was given by a scientist called Sir Ricardo. So he is a scientist of engine research. He has given the names for the stage 1, stage 2, stage 3. Now let us see here at stage 1 what is happening. Already we have discussed at point A, the spark initiation will be done. At point B, combustion initiation will be done, right? That period is called ignition lag. In the second stage, at point B, the combustion is initiated and because of the combustion initiated, the charge present in the cylinder, it tends to combust immediately and pressure increases at a very fast rate, where we can see the maximum pressure rise until the point C. Now from B to C, it is the second stage, and that second stage is called flame propagation or propagation of flame. Now coming to the third stage, after reaching the maximum pressure, the piston will be moving towards the BDC, that is called expansion stroke. Now during that stroke, what happens, if there is any fuel particles left, that will be burned. That is called as third stage, and that name is after burning stage. Now these are the three stages in the SI engines: ignition lag, flame propagation, and after burning stage. Now let us see in detail what happens in each stage. Now let us start with the ignition lag. Now what is meant by this ignition lag? It is a time interval between the initiation of spark and the start of combustion. Initiation of spark and start of combustion is called, so initiation of spark and start of combustion. When the combustion is started, we can see a small rise in the pressure, that is a noticeable rise in the pressure we can found at point B. So it is a time interval or the time period between the instant of spark or spark initiation and the noticeable rise of pressure, that is called ignition lag. And this, what happens in this ignition lag is after spark has been created, the charge present in the cylinder, it attains the heat from the spark, so that it will reach its self ignition temperature. So the molecules of the charge, it is getted heated by the spark, so that it will reach its self ignition temperature and it will ignite itself by creating a flame. And that flame will be propagated. So here this is what happens in the ignition lag. Now what is the time interval of the ignition lag? It is very less, that is 2 milliseconds. So this ignition lag generally depends on so many parameters, like what type of fuel we are using. That is, in SI engines we will be using gasoline, also we are using the CNG gases. So based on the fuel properties, based on the nature or the properties of the fuel and the temperature and the pressure of the fuel and also the exhaust gases present in the cylinder, based on these parameters, this ignition lag time will be dependent. Now that is about the ignition lag. Now comes to the next stage, second stage, that is flame propagation. Now what happens in this flame propagation is, at point B, the combustion is initiated here. That is, combustion has started at point B. Now what happens here? The combustion, what happens here? Now let us see the diagram here. Suppose this is a cylinder. This cylinder will have a piston. Thus piston is traveling towards the TDC. Piston is traveling towards the TDC during the compression stroke. Now the charge which is present inside the cylinder, it is getting compressed. The charge which is present in the cylinder, it is getting compressed. Now what is the charge in the SI engines? It is a mixture of air and fuel. Now the spark plug, there will be a spark plug here at the cylinder head. When the piston reaches near to the TDC, the spark plug initiates the spark. Already we have discussed, that is a stage 1. Okay, the spark plug initiates the spark, which creates that spark plug initiates the spark, and because of the spark initiation, a flame is created. First, a flame is created. And that flame is called as flame front. Now this flame is surrounded by the compressed air fuel mixture. Now this the unburned particles will be burned by attaining the heat from the flame front. So in this way what happens, the flame will be propagated to the next level. So in this way again the next flame will be created. So all the fuel particles will be burned because of the flame propagation. So because of the flame propagation, all the fuel particles will be burned, which releases the high heat energy. Because of that, the pressure will be rising at a very fast rate, where we can see at the point C we can get the maximum pressure. So from at point B, the combustion is initiated and the flame is propagated from one end to the other end, and after combustion of all the charge we will get the maximum pressure at point C. Okay, now during this stage what happens, during this stage the flame will be propagated. The flame propagates at a constant velocity. And what is the level of rise of the pressure? Here is the level of rise of the pressure is directly proportional to the heat release. That means if the heat release is more, then we will get a higher pressure. So if the heat release is less, then we will get a lower pressure. So here the rate of pressure rise is directly proportional to the rate of heat release. This is a second stage of combustion in the SI engine, that is propagation of flame. And the third stage is after burning stage. In the third stage means what? After point C. Now after point C, the piston will be moving towards the BDC by increasing the volume. Now during that stage, generally the pressure will be decreasing. But in this stage what happens is the leftover fuel particles will be burned. So here very less fuel particles are present. That's why here there will be a lower flame velocity, and also the reduced flame front surface will be there in this after combustion stage. Now because of this, there is less fuel particles, there is no pressure rise. So because of in the after combustion stage, what happens, there will be lesser fuel, unburned particles will be left in the cylinder, and the piston will be moving towards the BDC during the expansion stroke, which leads to no pressure rise during this stage. And this stage is, that's why it is called as after burning stage. Now let us see a small video where we can clearly get the stages of combustion in SI engine. Okay, now how combustion takes place in an ideal engine, right? During the compression stroke, what happens? During the compression stroke, at the end of compression, the spark is initiated. Because of that compression process, the pressure will be increasing to the BDC. After that, the combustion is done. Because of that combustion process, the pressure will be increasing to a maximum value. Then expansion takes place. Because of the expansion, the pressure will be decreasing. So this is what a theoretical P theta diagram. It is not exactly happens in the actual engines or the actual conditions. Then how it is happened in stages, that is defined by Sir Ricardo. He is the father of the engine research. So he has made the combustion into the 3 different stages, that is ignition lag, flame propagation, and the after burning. In the first stage, it is called as ignition lag. It is a time period between the spark and the first flame. Spark and the first flame is called the ignition lag. It is also called as the preparation stage. Now let us see here, during compression process, during compression process, first spark is done, then the flame is done. This is called ignition lag. Next one is the flame propagation. In the flame propagation, the flame will be propagated from one end to the other end by combustion of all the fuel particles present in the cylinder, which increases the pressure. So here in this stage, burning rate and the flame speed will be less, whereas the pressure will be increasing continuously to its maximum value. Now after this stage, the next stage is after burning stage. In the after burning stage, what happens? The leftover fuel particles or a unburned fuel particles in the cylinder, it will be burned during the expansion stroke that the piston will be traveling from TDC to BDC. In this, the rate of combustion is less and also pressure will be less because of the less fuel particles present. Now let us see the pressure crank angle diagram. Now the y-axis is the pressure, x-axis is the crank angle, where the pressure increases continuously to its maximum value, then it decreases. In this graph, we can locate the point P, that is the start of the spark, point Q, that is a flame starting, that is initiation of spark, R is the maximum pressure reach, then S is the end of the combustion. Now by discussing all these concepts and when we combine all these concepts with the stages of combustion, we can able to write the names that was given by the Sir Ricardos, that is PQ equals to ignition lag, QR equals to flame propagation and RS equals to after burning phase. Now this is about the stages of combustion in SI engine. Now let us see the combustion, if it is a normal combustion or a abnormal combustion. So in the SI engines, the combustion can be a normal or a abnormal. Now what is meant by normal combustion? Whenever a spark is created and the flame is generated, the flame travels inside the cylinder evenly and by covering all the combustion chamber. That is, if the flame travels evenly across the combustion chamber, that is called as normal combustion. What about the abnormal combustion? In this, the combustion process is deviated from the normal combustion behavior. Because of the deviation, there will be a loss of performance and also damaging of the engine takes place. Now how that deviation happens in the case of abnormal combustion? Now here let us see this picture. In this picture you can see the flame is traveling evenly and uniformly in all the directions in the combustion chamber, whereas in the abnormal combustion we can see along with the normal combustion there are multiple flames been created in the circle area. The multiple flames are created which causes the knocking, that is called a abnormal combustion. Now let us see what are the reasons for this abnormal combustion. The first reason is pre-ignition and the second reason is knocking. Now what is the meaning of this pre-ignition? Now generally what happens in the SI engines, when the piston is moving from BDC to DDC, BDC to the TDC during the compression stroke, at the end of TDC the spark is created, that is a normal combustion. But during the same moment, that is the piston is moving from BDC to TDC, first a small amount of fuel particles will be ignited before the normal combustion. That is, in this figure we are having two flames. At the bottom near the piston there is one flame and near the spark plug there is another flame. Now this flame is created. The particles which are near to the piston, that particles tends to ignite itself, that is a pre-ignition. That is, ignition happens prior to the normal combustion, that is pre-ignition. Now after this pre-ignition, piston will be continued to the move towards the TDC, then the normal combustion happens with the help of the TDC. Now what happens, this flame and that flame will be collision takes place and that will be causes a abnormal combustion. That is what a pre-ignition means. Then what is a knocking is? Knocking it is due to the auto ignition of the fuel, Now how the auto ignition happens? Now during the compression process, at the end of compression, when the piston reaches TDC point, when the piston reaches the near to the TDC point, the spark plug will initiate a spark and a primary flame will be created. Here the green color thing you observed, this is a primary flame which is created. Now because of this flame, a compression is carried out to the corner particles and it will start a secondary flame. So in the case of knocking in the SI engines, firstly the primary flame is created with the help of a spark plug and auto ignition happens to some particles. Because of that, a secondary flame will be created. Now these two flames collision takes place. Because of that, there will be a loss of performance and damage of the system. Now let us see in detail of the pre-ignition and the knocking. So here what happens in the pre-ignition, as we discussed, first a ignition of some particles takes place, then the normal combustion takes place. That is what the pre-ignition. Then how that pre-ignition takes place for some particles. They will be in contact with the hot surfaces. They will be in the hot surfaces. So here the homogeneous mixture of charge will be in contact with the hot surfaces, which leads to the pre-ignition during the compression stroke. Now what are those hot surfaces? Here is because of the continuous running of the engine without proper cooling system and without proper maintenance, what happens inside the engine, the components like piston, cylinder, valves and the spark plug, it will be continuously absorbs the heat and it will remain as a hot surfaces. So here the hot surfaces means what? The spark plug electrodes, valves and a metal corners, and also this pre-ignition happens because of the carbon deposits. So when during compression stroke, these metal components are hot and the charge will gain the heat from these metal components because as they are hot surfaces, and it will gain its self-ignition temperature, then it will explode itself, it will auto-ignite itself and it will create a flame. Now after that, the normal combustion happens in the case of SI engines, and because of that auto-ignition continuously, it will overheat the spark plug. It will be overheating the spark plug and the exhaust valve, and it will remain as the hot, which will damage the system. So because of the pre-ignition, the engine efficiency will be reducing. Like if you see in this figure, that is premature combustion, when the compression is happening, initially at this point the combustion takes place. That is, suppose if the piston crown is hot, this is a hot surface and the particles will be in contact with the piston crown and it will explode. That is, explosion happens here. Now after that, the normal combustion is happened with the help of the spark plug, by which these two flames collision takes place and it will reduce the efficiency, of the engine. So reduces the efficiency of the engine, and it also causes the damage to the engine by making the holes on the piston and also melting the spark plug electrodes. In this picture we can clearly see, because of the pre-ignition, what happens, the electrode is overheated. Electrodes of the spark plug will be overheated. After some time the melting of the electrode happens, which will decreases the efficiency of the engine, and because is it continuous like that, it leads to the damage of the engine. That is, here you can see there is a hole in the piston. The pre-ignition leads to the damage of the engine. Okay, now that is about the pre-ignition. Now comes to the concept of the knocking. This knocking concept is very, very important in examinations. It was asked multiple times in the examination. Now let us start this knocking. So here, for suppose this circle is a cross section of the combustion chamber. Now at point A, the spark is initiated and it is created a flame, and that flame is called as flame front. That flame is called as the flame front. Okay, now this flame is called as the first flame which is created by the spark creation is called as flame front. Now this flame front will be propagating, it will propagates like this. So when it is propagating, that is when it is traveling from one end to the other end, that is it is traveling from A towards the D, it will be expanding, it will be expanding. Now because of the expanding, the particles present at the corner, that is inside the combustion chamber, the particles present at B, B dash and D, the B, B dash, B dash and D, the particles present at the corner of the combustion chamber will feel a compression, and because of that compression its temperature will be increasing. Now, so because of the flame propagation, it is expanding, these particles will be feeling a compression and its temperature will be increasing. Now if the temperature of the particles present in this B, B dash and D has not reached its self ignition temperature, so if the temperature of is not reached its self ignition temperature of the particles present here is B, B dash and D, then what happens? The flame which is propagating inside this, the flame which is propagating like this, it will consume this charge also. The flame will be consuming this charge, thereby generating the heat energy. This will be continued. Now if the temperature is reaches its self ignition temperature, now what happens is, now see here in this figure you can see the flame is propagating from the spark plug towards the other end of the combustion chamber. Now because of this flame propagation, the corner particles, the other end particles, it will feel a compression force, and because of that it will reach its self ignition temperature. When the self ignition temperature has reached, it will create a secondary flame here. Now the primary flame is created with the help of the spark plug, and the secondary flame is created because of the auto ignition of the particles, right? Now these two flames collision takes place, right? That collision, because of the collision of the two flames, it will increase its pressure rise in the cylinder. Not only that, a high intense vibrations will be created. Because of the high intense vibrations, the vibrations will hit the cylinders and piston, which will damage the system here. Now where it is possible, in a diagrammatical way we can see here from A onwards, the primary flame is propagating, whereas at point D it has reached self ignition temperature. Another flame will be traveling in an opposite direction. Both flames will be collision takes place at C and C dash. Because of that collision, a high intense pressure vibrations will be created, which hits the cylinder and piston, which damages the engine, and also by which the performance of the engine will be decreased here, and that is indicated in this P theta diagram. Here you can see initially in the normal combustion we have seen the diagram where it is a uniform and a smooth curve, but because of this knocking effect there is a disturbances in the normal combustion. That is why it is indicated with the help of the zigzag lines. Now so that this condition is called as knocking. So because of the hitting of the two flames, it will release a vibrations and it will hit the engine. That concept is called the knocking. That concept is called the knocking in the SI engines. Okay. Now let us see, we said that there will be an engine damage, where we can see here because of the knocking the piston crown is damaging, and also here we can see the piston crown is damaging. and we can see here the cylinder gasket and also the cylinder head. So all these parts will be damaging takes place because of the knocking in the SI engines. This knocking is called as the detonation. This knocking is called as the detonation in SI engines. This knocking is called as the detonation, okay, in SI engines. Now let us see the two P theta diagrams, which is represents the abnormal combustion because of the pre-ignition and also because of the knocking. Now this graph, this P theta is because of the pre-ignition, whereas it is because of the knocking. Now in these two P theta diagrams, we can see that there will be a disturbances inside the combustion chamber, that is represented by this zigzag lines. But here the important thing is the pre-ignition leads to the knocking. The pre-ignition leads to the knocking, where in both pre-ignition and knocking we will be having a abnormal combustion in the SI engines. Now let us see a small video. We can understand the knocking and the pre-ignition. Now first see the regular combustion, how it is happened uniformly and evenly. Now in this video we can see, now the exhaust is happening. After exhaust the intake will be happen, that is piston will be moving towards the BDC. Now after that the piston will be moving from BDC to TDC. While it is moving from BDC to TDC, the charge present in the cylinder getting compressed. When after that the spark is created, combustion is done, then exhaust will be happen. The suction, compression, expansion and exhaust. This will be happened uniformly without any disturbances in the case of regular combustion. But because of the abnormal combustion, in the case of knocking, what happens? First, a primary flame is created with the help of a spark plug, which leads to the creation of secondary flame because of the auto ignition of the particles, and the collision of the particles, two flames takes place, which creates a high intense vibrations inside the cylinder, which damages the system and also decreases the performance of the system. Now see here, first suction takes place, then the compression is happening. During this compression happen, first primary flame is created with the help of a spark plug, which leads to the secondary flame. Okay, so here the green color one is a primary flame and the blue is a secondary flame. Now these two flames collides each other, which creates disturbances in the combustion process, by which a vibrations will be created. It will hit the cylinders and all the engine components inside and damages the cylinder, and also it will decreases the performance of the engine. So after that combustion process, because of the knocking, again expansion takes place. The piston will be moving towards the BDC, then exhaust will be takes place. So this is what happens. Now coming to the pre-ignition, the pre-ignition is because of the glowing hot spot. The glowing hot spot is nothing but the hot surfaces, and also it is because of the carbon sediments. The carbon sediments are formed in the engine because of the long run. Now in this you can see the carbon deposits on the exhaust valve. This carbon deposits transfers the heat. Now when the compression is happening, this air fuel mixer will be in contact with the carbon deposits, which causes the combustion and it leads to the pre-ignition. This is one of the reason in the pre-ignition. And the next one is because of the glowing spark plug. That is, in the engines, in the spark ignition engines, the spark plugs are designed in such a way that the heat will be dissipated continuously towards outside to have a efficient working of the spark plug. Because of the over tightening of the spark plug, the heat which is coming from the electrodes, which will not be dissipated out, so it will be remain in the electrode itself. So it converts into a hot glow plug. That hot glow plug will be in contact with the charge, and during compression process it will cause a pre-ignition, then the normal spark will be created. Okay, now in this way the spark plug also creates a pre-ignition. Now how it is to be reduced? By the proper tightening of the spark plug for a particular torque, we can able to reduce the pre-ignition. Now here the pre-ignition leads to the knocking, and also the detonation is also called as a knocking. Knocking, that is collision of the two flames. Now because of the long term, that is collision of the two flames, you can, in this video you can see the two flames are collision takes place, which is damaging the piston crown. A hole is formed on the piston which is damaging the engine. So in this way the knocking and the pre-ignition happens in the SI engines. Now let us see the differences between the pre-ignition and the knocking. As what is here the pre-ignition means? Pre-ignition means this homogeneous mixture of charge will be in contact with the hot surfaces, which leads to the pre-ignition. Whereas in the case of knocking, the knocking is happen because of the auto-ignition of the unburned charge present in the combustion chamber during combustion process. Now what are these hot surfaces here? Hot surfaces is nothing but the spark plug electrodes, exhaust valves and the metal corners, and also because of the carbon deposits it leads to the pre-ignition. Then how here auto ignition happens? Here auto ignition happens because of the increase of pressure and temperature, of unburned charge during the combustion process. It will reach its self-ignition temperature and it will auto-ignite. That is called knocking. And here because of the pre-ignition, this pre-ignition leads to knocking, which will damage the engine and also decreases the performance of the engine. Whereas here in the case of knocking, because of the knocking, a high rapid release of energy takes place because of the auto ignition, which creates vibrations and a pinging sound. Which creates vibrations and also pinging noise in the combustion chamber, by which the engine performance will be decreased and engine damage takes place. These are the differences between the pre-ignition and the knocking. Now let us see the importance of the flame speed and effect of engine variables. First we have to understand what is this flame speed. Now when a flame is created with the help of a spark plug, that flame will be traveling from TDC to BDC. That is in the combustion chamber, it is traveling from one end to the other end. While it is traveling, the flame speed should be high, and when the flame speed should be high, it will complete the combustion process in a less time. Now what are the engine variables which affects the flame speed? These are the engine variables. The first one is the turbulence, Next is the air fuel ratio and temperature and pressure inside the cylinder, and the compression ratio of the engine output, engine speed and engine size. These are the engine variables by which the flame speed can be increased or decreased. Okay, now let us see about the turbulence here. What is the turbulence in the case of IC engine? Here the turbulence is nothing but creation of the movement of the particles inside the cylinder. Movement of the particles. If there is a movement of particles inside the cylinder, it leads to a higher flame speed. When there is a higher flame speed, it causes combustion time to decreases. So there will be a efficient combustion in the SI engines. For example, see here, if inside the engine, if it is a laminar flow, that means all the particles will be flowing in a laminar. So because of that, it causes a higher flame speed. Now because of the turbulent flow means there will be a momentum to the particles present in the cylinder, momentum to the particles. So because of the momentum to the particles, it will create a higher flame speed so that the combustion can be done at a very faster rate. Now here how this turbulence or the air movement is created. By changing the design of the some parts in the cylinder, we can able to create the air particle movement inside the cylinder. Now what are those parts? We can able to change the design of inlet pipe or the valve openings. In the suction stroke, we can able to change the direction of the charge travel. Suppose if you see in this figure, if there is no air movement or the particles momentum from the inlet manifold, the charge will be directly entered into the cylinder. But when we change the design of a inlet valve or a intake manifold, what happens? It will attain a air movement, or the charge particles will attain a movement. Because of that, the flame speed will be increasing. Now see here, when we change the design of the particular manifold or inlet valve, here you can see the particles are having a movement, that here it is having a spiral movement or a helical movement. In this way we can able to mix. So when the particles are moving in that direction, what it makes to increase the flame speed is, because of this moment, the uniform mixing of the air and fuel will be possible. When there is a uniform mixing, it leads to the proper combustion, efficient combustion takes place, and it causes higher flame speeds in the engine. Now this creation of the particle or the charge particles movement, it can be done in two ways. One is swirling movement, another is tumble movement. What is swirling movement is the charge or the air fuel mixture which is entered into the cylinder, it will flow in a direction by maintaining a spiral path or a helical path like this. That is, if the charge enters into the cylinder with having this spiral or a helical path, then we call it as a swirling motion. Now what is tumble here? Tumble in the sense, the charge particles or the air fuel mixture, it will have a radially inward. That means it will radially move inside itself. So radially inward motion takes place. That is called tumble motion. It is also called as squish motion. So because of this turbulence, what happens? The flame speed will be increasing, and it minimizes the tendency of the abnormal combustion. Now coming to the next one, that is air fuel ratio. Now this generally the highest flame speeds are obtained at slightly rich mixtures, because when we use a lean mixtures in the sense, the fuel content will be less. So in that case, what happens? The fuel particles will be distributed far to each other. So because of that, what happens? The flame speed will be decreases here in the case of lean mixture. So that is the reason, to have a higher flame speed, it is advisable to use a slightly rich mixtures in the case of IC engine. Now comes to the intake temperature and pressure. Now when the intake temperature and pressure is higher, means the proper mixing of air and fuel takes place. So because of that proper mixing, we can able to increase the flame speed. So if the initial pressure and temperature is high, it causes better homogeneous air fuel vapor mixture, which increases the flame speed. So here flame speed increases with the increase of pressure and temperature. So that is the effect of the inlet pressure and temperature. Now comes to the effect of variable compression ratio. What is compression ratio? We have discussed in the last session only. But what happens when we increase the compression ratio? The inside cylinder pressure will be increased because its density will be increasing. Now when the cylinder pressure will be increased, what happens? It causes again a homogeneous mixture, where uniformly distributed mixture takes place by increasing the density of the particle. Now during this process, when we increase the compression ratio, there will be a increase in the peak pressure and the temperature, and because of that the flame speed will be increasing, and it leads to the combustion duration to be reduced. That is, when the compression ratio of a SI engine is increased, it leads to increase the pressure and temperature, thereby we can able to increase the flame speed. Finally, the duration for the combustion will be reduced. So thus engines having a higher compression ratios will have a higher flame speeds. Okay, now comes to the other variable called engine output. So when the engine output is high, for suppose the engine output is high, means inside the cylinder the pressure is high, inside the cylinder the pressure is high. So when the cycle pressure increases, when the cycle inside the cylinder, when the cycle pressure increases, automatically it causes to increase the flame speed, it increases the flame speed. So when the engine output is increasing, means it is inside the cylinder the flame speed is also increasing. Now according to the engine speed, when the engine speed is increasing, the piston tends to reciprocate at a very faster rate. Now because of the weight piston reciprocating at a very faster rate, the above the piston we will be having the charge, that is the particle, air and fuel particles, they tends to move each other. That means a turbulence is created inside the cylinder. That is, when the piston is moving, it creates a turbulence inside the cylinder, which because of that turbulence a proper mixing takes place, and because of that proper mixing the flame speed can be increased. And we can say that the time required for the flame to transfers from combustion space will be halved if the engine speed is doubled. That is, if the engine speed is doubled, we can inside the cylinder the flame can travel in a half time. That is what happens when the engine, with respect to the engine speed and the flame speed. Now comes with the effect of the engine size. With respect to engine size, there will be no much effect, but when we can say that when we increase the size of the cylinder, when we increase the size of the engine cylinder, what happens during combustion process, the flame has to travel this long distance. So because of this long distance, the combustion time will be increasing, here. So the larger in the larger engines, the time required for the combustion will be 4, because the flame has to travel longer distance. Now these are the variables which affects the flame speed. Now in SI engines, to have a efficient combustion, the flame speed should be high. So that is what the effect of the engine variables in the SI combustion chamber. Now let us see different types of combustion chambers in the SI engines. Here we are having various types of combustion chambers. Here, why we are having various types? Because from the invention of the SI engine, the technology is changing, the advancements are happening. As the advancements are happening, the combustion chamber and the piston design are continuously changing. So these are collaborated and says that we are having different types of combustion chambers. So let us see what are the different types of combustion chambers. Here the types of combustion chambers are differentiated by change in the design of the piston, which is present in the cylinder. Now over the years, what happened? Over the years, the engine was developed, and based on the position of the spark plug and the location of the inlet and the exhaust valves, we are having different types of combustion chambers in the SI engine. Those are T-head type combustion chamber, L head type combustion chamber and I head type combustion chamber. Finally, it is F head type the combustion chamber. Now let us start with the first one, that is T head type combustion chamber. In this T head type combustion chamber, it was found by the Ford in the year 1908. Now in this combustion chamber, there are two valves opposite to each other, inlet valve and exhaust valve, and the spark plug is placed on the cylinder head, placed at one corner. Now in this, it requires a individual camshaft to run the two valves, which is difficult to manufacture, and there is a high chance of knocking. So what happens? In the World War I, this was used, and in the fire trucks till 1950s, this combustion chambers were used. And now after that, there is the end of this type of T head type combustion chambers. Now the L head type combustion chambers were introduced. This also found by the Ford company. Now in this L head type combustion chambers, what happens? This inlet valve and exhaust valve are placed on one side of the cylinder on a inline manner, whereas spark plug is placed at the center. Now because it is a one side, the valve mechanism is very simple, and also we can operate with a single camshaft in the cylinder, and ease of maintenance is also high. Now other than these advantages, there is a big disadvantage here is, here the valves are placed at this corner and spark plug is placed at this corner in the head. There is a much chance of knocking. So to avoid that, Sir Ricardo has changed the size design of the cylinder head into this curvature shape. Now the spark plug is shifted to the exactly opposite to the inlet and exhaust, by which we can able to reduce the knocking effect. When the knocking effect is reduced, the combustion can be done in a very efficiently manner. So this type of combustion chambers were used. Now after that, I type combustion chambers came. That is in I type, over the cylinder head, the inlet valve and exhaust valves are placed, and the spark plug is placed at one side of the cylinder head. Now it is very simple in design, and mostly for small capacity engines, this type of is placed. This is developed by a scientist called Buick in the year 1950s. This overhead cylinders or the I-type cylinders can also be classified as two types. That is, first one is a bathtub type and the second one is a wedge type. Bathtub type, it will have a small oval shaped space, and in the wedge also there will be a space which is useful. The wedge shape will have a small space which is useful to take more amount of the charge for increasing its volumetric efficiency. This combustion chambers were used in the V-type engines. And what is the advantage of this I-type is less knocking, low emissions, high volumetric efficiency. Finally, it is F-type combustion chambers came. It is a combination of L-type and I-type. So here what happens, the valves are placed opposite to each other. One valve is placed at the side of the cylinder, another valve is placed on the cylinder head. Now because of this, there is a chance of knocking, and this F-type cylinder will having a rover model, as well as it will having another model called a Willis model. In both the models, we will have a higher volumetric efficiencies and also higher thermal efficiencies. So which requires in this a individual camshaft to operate the inlet valve and the exhaust valve. Now these are the types of combustion chambers used in the SI engine. Now with this, we'll stop the session today. Thank you all for watching this video.